Let's consider a case of a standing wave, but where the boundary conditions are different. Okay, and I'm going to use this opportunity to also talk about pressure waves versus displacement waves. So to start, suppose I have a tube. Okay, this could be a brass tube or a part of a musical instrument, a clarinet, a flute, a tuba even. We'll just keep it simple as just this tube. And at one end, the tube is sealed shut. The other end is open to the atmosphere. Okay. Now, by blowing over the edge or having some sort of mechanism to cause a vibration in the air that is inside this pipe, you can create a standing wave. But like the wave on a string, the geometry of this restricts the wavelengths that are possible. To get there, let's try and think about what's happening to the air molecules inside this pipe. Over against this wall, there's some air molecules. Okay, they're sitting there, and they are fixed. They can't move. The reason why is because they're next to this wall, and this wall is fixed. It's not moving. So the layer of air molecules right next to that wall cannot move. Whereas over here, when you look at the air molecules over here, they are open to the atmosphere and are free to move as wildly as they want. And so these molecules can move back and forth. Sorry, that is not a very good arrow. They can move back and forth as wildly as they want. So these two conditions are now opposite each other. Over here, the molecules are fixed in place. They cannot move. And these molecules can move wildly to maximum amplitude either direction. And so if we were to trace that on a line or look at a wave inside there, if we consider the displacement wave, okay, if this is displacement away from equilibrium, remembering that when we think of displacement, we think of the particle's motion away from its equilibrium point. And so these molecules cannot move away from their equilibrium point. They're stuck there. And so I have to have my curves, my waves have to go through the equilibrium point here at all times. Now over here, those molecules can move to either direction of their equilibrium point. And so they can move in a range over here from maximum to a minimum. So they have to end up going through this maximum minimum point to be able to achieve that. So over here, these molecules must be able to oscillate in the maximum extremes. Okay. Now, with that in mind, we can then start thinking about, well, what allowed wavelengths can I have to meet these two boundary conditions? Okay. The first case is the simplest one is just a curve that gently approaches that maximum. I could have done the minimum too, but just gently approaches that. And if this tube has a length L, we can ask, how big is the wavelength for this case? Now this one's kind of hard to see, but I'm starting from the equilibrium point and getting up to a maximum. Well, if I go from that maximum back to the equilibrium point, that would be half a wavelength, because I'd have to then go to the minimum and then back to equilibrium to reach a full wavelength. So this ends up being a quarter of a wavelength, or the wavelength is 4 times the length of this. Okay, so this is 1/4 of a wavelength, or I'm going to write a column heading here. Lambda for this case is 4L. Okay, let's do the next possible case. Here's my displacement wave, and here's the maximum and the minimum. It's got to go through the equilibrium point here, and it's got to be able to oscillate freely between these 2 points. Okay, so at one point in time, it's got to go from here to here. Alright, so how can we accomplish that in the next mode of oscillation? Well, I can go up and then down. And the question is, how many wavelengths is that, or what fraction of wavelength is that? Well, I'm going to just draw that, and I can see that that is 1/4 of a wavelength, like I had up here. Here's 2/4, and here's 3/4. Okay, so this is 3/4 of a wavelength. and that equals L, which means lambda is 4/3 L. Okay, lambda is still bigger than L. It's 4/3 L. So here's 4/3 L. Okay, next case, which hopefully you're trying to work ahead of me to guess what it's going to be. Again, it's got to go through this point here. It's got to be able to freely oscillate between the maximums here. And so if I draw that one up like that, and if I draw my lines here to mark the quarter cycles, okay, I see one wavelength goes to here, and yet there's another quarter cycle left. So there are 5 quarter cycles in this length. So this is 5/4 lambda, or the lambda is 4/5 of L. Okay. All right. Do we see a trend? If I put a little 1 right there, hopefully you do. If I did the next one, we could expect a 4/7 L for our wavelength. The integers are increasing but only by odds. So from this, we can infer a relationship. The modes, the wavelength modes, with this being the first mode, this being the second mode, okay. But we're gonna recognize that it's an odd integer, okay, for this pipe. The modes then are equal to, if I were to write this out, 4L over M, but M is equal to 1, 3, 5, ... Okay. And as was the case for our stringed instruments, we often, instead of talking about wavelengths in sound, we talk about the frequencies in sound. And so it's a little bit more convenient or profitable to talk about the frequency, which, again, that's equal to the velocity over the wavelength, or the velocity equals the frequency times the wavelength. And so just inverting that, we have mv over 4L with the same condition. M equals 1, 3, 5, ... Okay, now, in some textbooks, this might be n or something like that to differentiate it from the subscripts, but I would hope that you more focus on what the m means for the particular case. We know that the integer is odds only for the case of opposite boundary conditions, and then it's all digits for the same boundary conditions, and we didn't have 4L, we had the 2L. Okay, so this is now our relationship between the frequencies that we would hear when a piped instrument is being played that is open-closed, and that's all that's allowed. Now, what's interesting is how you generate that. Like when a flutist blows over her flute, the vibrations, the blowing over that causes all sorts of frequencies, but only these frequencies cause any significant displacement in there. All the other ones kind of dampen out. They don't go anywhere because the configuration of here restricts the wavelengths and thereby restricting what frequencies are allowed. I want to continue on and talk about a pressure wave. Now here we talked about displacement. We said that over here the molecules can't move. So that's a displacement node. They can't move. Over here it's a displacement anti-node. That means it can move wildly over there, and those are the conditions. Well, let's think about what's happening in terms of pressure. Sound is often best described as a pressure wave. The air molecules get squeezed together at higher pressure and then spread apart at lower pressure. So I'm going to draw this picture again a little bit bigger, just a piece of it, just this end piece right here, and think about what's happening to the air molecules. So this one layer of air molecules can't move at all. It just sits there because it's stuck against this wall. Okay, let's imagine at some time the air molecules are fairly compressed there. Like this. And then they might start getting closer together over here as we get this wave. So this is one moment in time where those molecules are being compressed here. Now that's a point of high pressure. These molecules are all being compressed here. This would be a point of low pressure because the molecules are spread apart. Okay. Now nature doesn't like that. It wants to try and reach equilibrium. So that means these are going to push apart later on, and these are going to get compressed together. So at a later point, push this up a bit. At a later point, this layer of molecules is still there, but now these molecules have gotten compressed over here. So you can think about this compression zone is moving along the pipe, and then this rarefied zone, that rarefication means that the molecules are spread out, this zone here starts moving out, and the cycle will keep repeating. And so we end up with a pressure wave that's traveling. Okay, now how do we relate that to this? We should be able to see the same thing. What happens is at this point right here, which we can see down here, the pressure is oscillating maximally. It can go from highest pressure to lowest pressure, highest pressure to lowest pressure. And so we end up with a pressure antinode wherever we had a displacement node. Now over here, this is open to the atmosphere. And the atmosphere has a constant pressure. And so these molecules can move freely, and there's no tendency left or right, because the air pressure is the same. And so this point right here is a pressure node. The pressure can't change there. So if I were to go back and look at this pipe, and I were to now draw a pressure wave, or describe the pressure as a function of position along the pipe, now I'd have the open end of the pipe be a node, and the closed end of the pipe be antinodes, pressure antinodes. But you can see it's the same thing. All these curves would just be backwards. I would get the same conditions for the length, the wavelength, and therefore the frequency that's allowed. But the pressure is describing a totally different thing than displacement. These molecules can't move, yet the pressure there changes wildly. These molecules can move wildly, but the pressure there can't change because it's open to the atmosphere.